Two robots, one grid, both falling downward at the same time, scooping up cherries. Your job, collect as many as possible. The catch? Their paths depend on each other. This is where flat tables stop working and a third dimension begins. This is the difficulty spike of the module, and honestly, a great one. Once you see how to track two travelers at once, three-dimensional dynamic programming stops being intimidating. Here's the setup. We have an M by N grid, and every cell holds some cherries, 0 or more. Robot 1 starts at the top left corner, Robot 2 starts at the top right. Both move down exactly one row at a time, simultaneously. From a column C, each robot can step to C-1, stay at C, or move to C+1. They collect the cherries on every cell visit. But here's the crucial rule. If both robots land on the very same cell, those cherries are counted only once. The goal is to maximize the total cherries collected by the time both robots reach the bottom row. So how do we describe the state of this system? Notice something important. Because both robots move down together, they are always on the same row. That one row index is shared between them. What still varies independently? Robot 1's column and Robot 2's column. So our state needs three numbers, the row, Robot 1's column and Robot 2's column. We define f of r C1, C2 as the maximum cherries collectible from row R down the bottom, with Robot 1 at column C1 and Robot 2 at column C2. The final answer is simply f of 0, 0, n-1. That's both robots at the top in their starting corners. Now the recurrence. First, the cherries we gain on the current row. We always add Robot 1 cell. We add Robot 2 cell only if they are on different columns. That single condition encodes our counted once rule. Then, each robot independently picks one of three moves. 3 choices for Robot 1 times 3 for Robot 2 gives 9 combinations in total. We try all 9 and keep the best. So f of r equals the gain on this row plus the maximum over all 9 next states in the row below. At the very last row, there are no moves left, so the answer is just the gain. And any column that falls outside the grid is invalid, treated as negative infinity, so it's never chosen. Let's turn this into code. For a three-dimensional state like this, memoized recursion is the cleanest form to write and read. Watch how directly the math becomes code. First, we guard against invalid columns returning a large negative. Then we check our memo table. We compute the gain with the counted once rule. At the last row, we return the gain. Otherwise, we loop over all 9 moves, take the best, add the gain, and cache the result. We start the whole thing with f of 0, 0, n-1. The memo table is m by n by n by n, all initialized to -1, meaning not yet computed. Let's count the work. The number of distinct states is m times n times n. Each state does a constant 9-way transition. So the time is order m times n squared. Memoized space is also m times n squared. But since each row only depends on the next, you can keep just one plane and shrink space to order n squared. A bottom-up tabulation does exist. You'd fill the table from the last row upward using the same 9-way transition. But here's an honest teaching point. For a three-dimensional state, memoization is usually the cleaner thing to write. Don't force tabulation when recursion reads better. 3 pitfalls to watch. 1. Don't double count. Only add Robot 2's cell when the columns differ. 2. Your invalid column sentinel must be a large negative, not -1, since -1 means uncomputed. 3. Never try to put the robots on different rows. They always share a row, and that is exactly what keeps the state 3-dimensional instead of 4. Here's the takeaway. More agents or more moving parts means more state dimensions. But the method never changed. Define what varies, write down the choices, then combine. A 3D problem is really just a 1D problem with 2 more indices. And that wraps the grid arc. We went from a second dimension for a last choice to position states with counts, guards, and costs, to fixed versus variable endpoints, and finally a third dimension for 2 travelers. The transferable move, collapse tables to rows for space, and let your endpoints decide the fill direction. Next, we leave grids behind for the richest pattern in all of dynamic programming, choosing subsets and subsequences, starting with the knapsack family. Practice this one by hand on a 3 by n grid first. See you in the next one.